All right, so welcome to Physics Video 3.6. We're going to learn today about what are called free body diagrams. So here's what a free body diagram is. It's just a drawing of an object with all of the forces labeled on it at one specific instant in time. All right, two strong words of emphasis. First of all of the forces. So that means you need to account for every single force that's acting on the object. Secondly, it's at one specific instant in time. Okay, so it's like a snapshot. You've taken a photograph of this object, and at the instant that photograph was taken, here's all the forces on it. All right. In addition, the drawing also includes the following information sort of written off to the side. You're going to write down what the net force is, you're going to write down what the acceleration is, and then any information about the velocity. Ideally, the velocity at that instant. Sometimes we'll include the initial and final velocity if that's sort of persisting. That'll become clearer as we go through more examples. So we've already made some drawings like this, but so far all the examples that we've done have only had horizontal forces since the objects were being pushed horizontally. Since the motion was horizontal, we didn't need to worry about the vertical forces like gravity and some others that we're going to learn about here. However, in the real world, we almost always have vertical forces because we almost always have gravity, right? I mean, 99.9999% of the time, a problem that you solve is going to take place here on Earth, right? And so gravity is always going to be an issue. All right. So we've already talked about force of gravity. So it says here there's some definitions. I think I've already taught you that. So I don't think we actually have some definitions. But I did make this list here, which is basically kind of the steps that you're going to follow for making a free body diagram. Okay? So let me move this guy out of the way. Kaboom. There we go. All right. So general process for making a free body diagram. The first thing you always want to do is draw your object. Again, just a box or a circle is fine if you are, you know, uncertain of your artistic abilities. So draw your object. You're going to write down the mass of the object. Remember that always goes inside the object. All right, and then find your force of gravity. Remember, you can always calculate your force of gravity using this guy, or conversely, if I give you the force of gravity, you can find the mass by using this guy. Okay? Every single problem, I'll either give you the weight or the mass of the object, and then you just got to find the other one. All right, so that's always your first step. Draw your object and identify your mass and your weight. Second step, label any forces that are given. So if it says, you know, Roy pushes the box with a force of 10 newtons, then draw the force of Roy of 10 newtons. If it tells you friction is 8 newtons, then put in your force of friction. All right? This third step is the tough one. Okay, because a lot of times what people do is they stop at step 2. All right, you have to think, and I don't mean this to be condescending, but you got to stop and think about what you know. All right, so if you know the acceleration of the object, you're going to do these two things. All right, I should comment real quick too. Sometimes it won't outright tell you what the acceleration is, but you'll know it because, for example, if the object isn't moving at all, or if it's got a constant velocity, you know your acceleration is 0. So keep that in mind. All right, so if you're able to, based on the context of the problem or what's given, if you're able to figure out the acceleration, then once you've done that, use Newton's second law to find your net force, right? In other words, do net force equals mass times acceleration. And then once you've done that, you can use this equation. You know your net force. So if you're missing any forces, like maybe you don't know, you know, the force of friction, you can use that equation there to solve for any unknown force. All right. The other possibility is sometimes in the problem, it'll just give you all the forces. And so if that's the case, then you can use the definition of net force to find the net force. Oops. In other words, add up all your forces and find your net force. And then once you've done that, find your acceleration. Okay? So that's really quickly kind of the general process. My suggestion is write this down and sort of keep it off to the side. So as we run through examples here, you can kind of keep that handy. Okay? I am going to go through a bunch of examples. My goal is to get through kind of one of every sort of type of example that you might see in class, but I also want to remain true to my promise to stay under 15 minutes or so. So I might skip a couple of the examples as we go, depending on how time permits here. All right, so here we go. Example number 1, a 6-kilogram cat named Gordon jumps out of a tree. So it says to make a free body diagram of Gordon while he's falling. All right, so draw your object. Cat. All right, there he is, 6 kilograms. That's your step 1. Identify your mass and your force of gravity. So somewhere off to the side, calculate your force of gravity. right? 6 kilograms times negative 10 meters a second squared. So you get negative 60 newtons. So your force of gravity pulling the cat down is negative 60 newtons, right? It's just the mass times negative 10. I'm going to stop writing this out every time. I'm going to assume if I give you the mass, you can find your force of gravity. Okay. All right, so the cat is falling. So that was our step 1. Step 2 is identify any given forces. So it doesn't say anything about Roy pushing it. There's not any friction because he's not sliding, right? So I think that's it. That's our only force. So our step 3, there's actually a couple of ways you can do it. We automatically know our acceleration, right? He's in free fall, so the acceleration is going to be negative 10 meters a second squared. And our net force is the total of all the forces. Well, the only force is the negative 60 newtons. And you can double check that, right? Acceleration equals net force over mass. My net force is negative 60 newtons. My acceleration is negative 10 meters a second squared. I'm sorry, my mass is 6 kilograms. Sorry, I'm trying to hurry, and as a result, doing a rotten job. So when you divide that out, you get negative 10 meters a second squared, right? Squared. All right. So there wasn't a whole lot to this one. I can't write down the velocity because the velocity is constantly changing. So in this one, we're kind of done. So here's my drawing. The drawing is the object with all the forces, and then the acceleration and net force written down. So everything I just put a red box around, that's my drawing. Okay, let's move on to another example. All right, it says Roy holds a 14-kilogram box in his hands. Make a free body diagram. All right, so first of all, when you make a free body diagram, you're just drawing one object. In this problem, we're focused on the box. All right, so you don't need to draw Roy. All right, so here's the box. It's 14 kilograms. Step 1, identify your mass and your force of gravity. So the force of gravity is going to be 14 times negative 10, so it's going to be negative 140 newtons, right? So that's my step 1. Mass and force of gravity. Okay. Step 2, identify any given forces. It doesn't really tell us anything. It doesn't tell us how much force Roy is exerting, if any. I mean, hopefully it's clear to you that he has to be exerting some force because he's holding the box up. But it doesn't outright tell us that. So we really don't know a whole lot. So our step 2, we're kind of at a loss here. All right, so step 3 is think. So what's the box doing? It's sitting at rest, right? So in this problem, our velocity is 0. And arguably, more importantly, it's also constant, right? And it's important that the velocity is constant because that tells us that our acceleration is 0 and our net force is 0, right? So now that we know our acceleration and our net force, we go back to our drawing. This drawing can't be right. We know our net force has to be 0, but the drawing indicates that the net force is negative 140. So what's preventing the box from falling? Gravity is pulling it down. What's preventing it from falling? Well, Roy's holding it up, right? So there's got to be an upwards force from Roy. And the question is, how much force? Well, he needs exactly enough force to make the net force 0, right? So it would have to be 140 newtons, right? So there you go. There's your free body diagram. The most common mistake that I see people make is they'll make a free body diagram where the drawing doesn't agree with their given information. So please make sure once you write down what your net force is, make sure your drawing shows the same net force as what you're telling me the net force is. Okay, that'll become more apparent in some of the other problems here. Okay, so there we go. Next example. This is going to bring up a new term. Almost the exact same problem, but this time instead of Roy holding it, it's sitting at rest on a table. Okay, so I'm going to kind of plow through it. It's the exact same train of thought. Here's your box, 14 kilograms. Gravity's pulling it down with force of 140 newtons. Once again, your velocity is 0. It's constant. That says constant. Constant. Since your velocity is constant, acceleration is 0, net force is 0. That means there has to be something pushing it up. Well, what's preventing the box from falling? Oh, it's sitting on a table. So there's an upwards force from the table. And that force from the table has to be 140 newtons. Okay? All right, so new definition. The support force provided by the table, I should have retyped this in advance. Do you know what? I'm going to pause it right now. What do you think about that? All right, so here we go. The support force provided by the table or any inanimate object, an inanimate surface, is called normal force. All right, the idea is the box is sitting on something. We don't care what it's sitting on. We just know that it's sitting on something. And so instead of calling it FT for table or FF for floor or FD for the force of the desk, in physics we always just call it the normal force, FN. Okay, so FN from now on is the normal force, and that's the support force provided by whatever surface your object is sitting on. Okay, that's going to come up a lot. Anytime your object is sitting at rest on a surface, there's going to be a normal force of some sort. Okay, so I'm totally going to run over my time here. All right, well, here we go. We got a dog. So here we go, dog. Bloop, bloop. That's a dog. All right, 8 kilograms. Gravity is pulling him down with negative 80 newtons, right? So that's step one. He's being lifted upwards from rest, so off to the side. I'm going to write down my initial velocity is 0. Ed is lifting him with 80 newtons. So here's our force of Ed. This is our step 2 now, right? Write down any given forces. So we've got a force of Ed. It's 100 newtons. Okay? Problem tells you the time is 3 seconds, and we want to find out what the velocity is at the end of those 3 seconds. Okay? So now we're down to that next step where you've got to stop and think. Well, let's see. Do we know the acceleration? We don't. We know the dog is moving upwards, but we don't know anything about how quickly he's moving upwards, right? So do we know all of our forces? Well, let's see. Ed is lifting him. So we got our force of Ed labeled. We've got gravity pulling the dog down. What about a normal force? Because Ed is lifting the dog, he's not touching the floor or the ground or anything, right? So he's not sitting on any sort of surface. So there is no normal force. That's probably worth writing down. There's no normal force because the dog is not sitting on any surface because Ed is lifting him, right? So I think that's it. I think that's all of our forces. So we can find our net force by adding them all up. Our net force is the force of gravity plus the force of Ed. So for us, it's the negative 80 newtons from gravity, the 100 newtons from Ed. So our net force is 20 newtons. And now that we've done that, now we can find our acceleration by doing net force over mass, 20 newtons, 8 kilograms. So the acceleration is 2.5 meters per second squared. And so now you can find the VF by doing VF equals VI plus A times T. And you get 0 because he's going from rest, plus 2.5, I'm skipping units to save time, times 3 seconds. So after those 3 seconds, the dog is going to be moving at 7.5 meters a second. Okay? The big thing that I want you to notice here is this, that in order for Ed to lift the dog, his force has to be bigger than the force of gravity, right? That's what produces this net force that gets the dog moving upwards, right? Okay, so my final free body diagram would be everything to the left of that red line that I just drew. So I've got that. I need to write down my velocity. So the drawing began when the velocity was 0. My final velocity I just found at 7.5 meters a second. I should write down my net force, which is the 20 newtons. And I should write down my acceleration, which is 2.5 meters a second squared. Okay, so everything on that side of the red line is my free body diagram. Hopefully yours are a little bit neater than mine. Okay? All right. I'm going to do 2 more examples here, and then I'm going to stop, and we'll talk more in class. I'm going to go a little over 15 minutes, but I'm going to keep it under 20. All right? So this one is really similar to the last one because we're lifting the box again, but I'm giving you different information. Okay? So once again, we've got a box that's being lifted. All right? So here's our 30-kilogram box. You can always start by putting in your force of gravity. It's going to be negative 300 newtons, right? Just 30 times negative 10. Carl is lifting it, right? So there's going to be an upwards force from Carl. We just don't know how much, right? It says he lifts it, but we don't know how much force he's using. I do know the acceleration, though. That is huge. I also know that he's lifting it from rest. So the initial velocity is 0. Oh, I even know the time is 4 seconds. Hopefully you're seeing this and going, oh, I can find the final velocity. So we can do that. Right? So let's take a second to do that. VF equals VI plus A times T. So it's going to get to a velocity of 8 meters a second. But our drawing's still not done because we don't know the force of Carl. Okay? So let's do that. Let's find our force of Carl. So what we're going to do is, well, first of all, are there any other forces? There's no normal force because it's not touching a surface. There's no friction because it's not sliding on anything. So I think that's it. But the problem is we still don't know the force of Carl. So we do know the acceleration. So what I told you back a couple slides ago was if you know the acceleration, find your net force. So the mass of the box is 30 kilograms. The acceleration was, I've already forgotten, 2 meters per second squared. So our net force is 60 newtons, right? So now we got to figure out how much force does Carl need to make the net force 60 newtons. Please remember, this is not Carl's force. That's the net force. And Carl's force, you can either do it conceptually and go, well, I need 60 more newtons up than I have down. So since I have 300 newtons down, I'm going to need 360 up. Or if you prefer, you can use an equation. It's this. Net force equals the force of Carl plus the force of gravity, right? So our 60 newtons, which is our net force, has got to equal the force of Carl, which is my unknown, that's what I'm looking for, plus the negative 300 newtons from gravity. And solve it. Let's see, this is like minus 300, so I'm going to add 300 to both sides. And you get 360 newtons is your force of Carl, right? And that makes your net force 60. So this is going to be 360 newtons. That makes my net force the 60 newtons that I needed and gets us the acceleration we wanted, right? Okay. So in a lot of ways, these problems are like puzzles. You really got to kind of think about what do I know and how is it going to allow me to find the stuff I don't know. It's like a Sudoku puzzle for smarter people, all right, which is you. So there you go. All right, I'm going to do one last example here. I'm going to hold off on this one. This will be a good discussion point for class. If you want, write it down and try it. It'll be a good thing to see if you understand everything. There's something weird about this. Your normal force, here's the big thing I want to caution you on. Your normal force does not necessarily have to equal your force of gravity. Okay, in this example, your normal force actually turns out to be bigger than your force of gravity. So take a second, read this over, and see if you can figure out what the drawing looks like. All right, and I know I always say this, but we'll talk about it in class, and hopefully I'll remember. All right, same thing. We've already done one like this. Oh, no, we haven't. Here's one where Roy tries to lift it, but actually fails. So this is another one of those problems where your normal force does not equal your force of gravity. You know what? I guess I should probably just do this. Let's do it. Kaboom. So here we go, walrus. Can I draw a walrus? I don't know. There, walrus. All right, so he's got a mass of, I'm going to totally go over my time. He's got a mass of 300 kilograms. Gravity's going to pull him down with a force of negative 3,000 newtons, right? 3,000 newtons pulling this guy down. And Roy comes along and tries to lift him. Why Roy is lifting a walrus, I don't know, but he's going to try to lift him with a force of 500 newtons. So stop and ask yourself, if you've got something that weighs 3,000 newtons, is 500 newtons enough to lift him? No. So what's going to happen then is that's not enough force to lift him, right? He's sitting on the floor. We're not going to be able to lift him. So since we don't lift him, our acceleration has to be 0, right? Because he's not going to move because you can't lift him. That means the net force has got to be 0. So my drawing's not right because my drawing over here doesn't show the net force being 0. Right now I've got a net force that's down. So I need an upwards force to make my net force 0. That upward force comes from the normal force. The floor is still holding the walrus up, right? So the normal force here needs to be 2,500 newtons. Okay? And that way, 2,500 newtons plus 500 newtons cancels out the 3,000 newtons and makes the net force 0. Okay? Finally, this last example, the big thing I want you to understand, we've done problems like this one before. The big thing I want you to understand is you've got your pony here. You're going to have the force of norm on it. You're going to have the force of friction on it. Even though the pony in this case is moving left and right, there's still going to be a force of gravity of, in this case, negative 1,600 newtons. The pony's not moving down, so there has to be a normal force also of 1,600 newtons. So long story short, anytime you have a problem where the object is moving horizontally, your force of gravity and your normal force are going to cancel out, at least for the purposes of this class. All right, I'm going to stop there because I went over my promise to 20 minutes. I suck. Have a good day. Kabam.